Mixture adsorption and microporous crystalline materials such as zeolites and metal organic frameworks is commonly competitive in nature. The competition in mixture adsorption is usually in favor of the guest that has the stronger binding. With increasing pore occupancies, the smaller guest molecules are favored due to entropic effects, and the balance between enthalpic contributions, i.e. binding, and entropic contributions due to packing efficiencies dictate the competitive mixture adsorption characteristics that in many cases is adequately described by the ideal adsorbed solution theory. In this presentation, I discuss the concept of cooperative mixture adsorption. To set the scene for this presentation, let's consider the adsorption of mixtures of CO2 and methane in sodium X zeolite, more commonly termed 13X zeolite. Carbon dioxide binds strongly with the extra framework cations due to its strong quadrupole moment. If we compare the component loadings for mixture adsorption indicated by the filled symbols, the red circles are for CO2 loadings for mixture adsorption. The green squares are for methane loadings for mixture adsorption. We compare these with the corresponding component loadings for the unary isotherms indicated by the open symbols. The white spheres are for CO2. The white squares are for methane. We see that in the mixture, the CO2 loadings are practically the same as for the pure component, whereas for methane, the loadings in the mixture are considerably lower by about 1.5 orders of magnitude than the corresponding values of the pure component loadings. Put another way, in the competition for mixture adsorption, CO2 wins the battle hands down, and methane loses this competition the dashed lines are the calculations of the mixture adsorption loadings using the ideal adsorbed solution theory. The IAST also anticipates that methane will lose the battle for mixture adsorption. There are quantitative differences, albeit slightly, between the IAST predictions and the values determined from configurational bias Monte Carlo simulations, and this is due to inhomogeneous distribution of the guest molecules within the pore space. Further explanation is provided in this publication. This is normal behavior in the sense that we have comparative adsorption between CO2 and methane in 13X zeolite. A different scenario emerges for adsorption of water ethanol mixtures in DDR zeolite. DDR zeolite consists of cages with a volume of 278 cubic angstrom. Each cage is separated from adjacent cages by narrow windows whose dimensions are 3.6 and 4.4. These are 8-ring windows. Configurational bias Monte Carlo simulations for mixture adsorption are compared with the data on the unary isotherms in this graph, in which the component loadings are plotted against the partial fluid phase fugacity. The component loadings for mixture adsorption are shown by the filled symbols, red circles for water, green squares for ethanol. The open symbols are for the unary isotherms. We note that for partial fugacities in the bulk fluid phase lower than about 10 kilopascals, the ethanol loading in the mixture is practically the same as the ethanol loading for the pure component. On the other hand, we note that the water loading in the mixture is significantly higher than the water loading for the pure components. In other words, the mixture adsorption appears to yield significantly higher values of the component loadings for water as compared to the pure component. This enhancement in the water loading is commonly termed as a cooperative adsorption. The dashed lines are the calculations of the IAST, and we note that the IAST anticipates the phenomenon of cooperative adsorption of water, albeit only to a qualitative extent. The enhancement in the water loadings is due to strong hydrogen bonding between water and ethanol gas molecules, as evidenced by data on the radial distribution functions shown in the subsequent slide. In this graph, we plot the distances between oxygen and hydrogen atoms for pairs of water-water molecules, shown in red, pairs of ethanol molecules, shown in green, and water ethanol molecules, drawn in black. We note in all three cases there is a strong peak at distances smaller than 2 angstrom. These short distance lower than 2 angstrom is a typical characteristic of hydrogen bonding. So there is strong hydrogen bonding between water and ethanol. There's also hydrogen bonding between water and water and between ethanol and ethanol. Essentially, the water-ethanol hydrogen bonding results in a strong enhancement in the adsorption of water molecules because, as it were, water rides piggyback on ethanol, which is the most strongly adsorbed. But due to hydrogen bonding, water gets dragged along with ethanol into the pores and enhances its loading in the mixture. On the right-hand side, we plot the enhancement in the water loading as the component loading in the mixture divided by the component loadings for the unary isotherm as a function of pore occupancy. For water ethanol mixture adsorption in chabazite, yellow diamonds, DDR, blue triangles, ZIF8, red circles, faugisite, cyan hexagons, LTA zeolite, gray stars. For all these 5 adsorbents, the water loading in the mixture is significantly higher than that of the pure component for a range of pore occupancies shown here. So, cooperative adsorption leading to enhancement of water loadings is typical of water ethanol mixture adsorption in a variety of host materials. Further information is provided in these publications. So, cooperative adsorption appears to be a direct consequence of hydrogen bonding between the constituent guest molecules.